See, we just were deriving for Prandtl number greater than 1, which happened to be thin thermal boundary layer. We realized that U is going to be varying within the thermal boundary layer thickness. We got that as U infinity delta T by delta, and from there we got this del T by L cube, del T by, so let me just write this, this is not there, actually please note that this delta was extra here because this delta I have put it here. So we got this as del T by L whole cube is of the order of, you see here, nu by U infinity L is nothing but 1 upon REL into alpha by nu is 1 upon Prandtl number, and delta by L is nothing but REL to the power of minus half. We had derived this just in the last module. Delta by L is of the order of REL to the power of minus half. So that's what I have substituted. So I get delta T by L whole cube is of the order of REL to the power of minus 3 by 2 and PR to the power of minus 1. So del T by L is of the order of REL to the power of minus half PR to the power of minus 1 by 3. So in the previous derivation we had just showed Nu is of the order of L by delta T, that is delta T by L to the power of minus 1, that is it is of the order of REL to the power of half PR to the power of 1 by 3. So Nu is of the order of REL to the power of half PR to the power of 1 by 3. So this is what we get for Nusselt number. So this is the, we knew that, we had told that when we non-dimensionalize the momentum equation and the energy equation, momentum equation fetched as Reynolds number, energy equation fetched as Reynolds number and Prandtl number. That's why our delta T and Nusselt number are indeed the functions of RE and PR. You see now, the beauty of the scale analysis is that you can do the experiments and get this constant which is missing, but you definitely know to what powers you should be representing your data. So that is the strength of the scale analysis. Over to slides. So what are the, if you just see the slides, you can see that these are the, from the closed form solutions you get 4.92, 0.664, 1.77 for Prandtl number less than 1, 0.565 for Prandtl number less than 1, for Nusselt number equal to, similarly 3 and 0.332. I just would like to calculate these values for a Reynolds number of 10,000. Remember, for a flow over a flat plate, Reynolds number 10,000 is still laminar because critical Reynolds number is 2 into 10 to the power of 5. So length I am taking 1 meter as plate length. Delta by L equal to 4.92, square root of REL gets you delta is 4.92. Now for Prandtl number less than 1, I am taking a Prandtl number of 0.1. So I get 0.01, I am taking a Prandtl number of 0.01, that is 0.1 whole square. So delta T by L, if I substitute all of that, I get 177. So you see, for Prandtl number less than 1, we had said that delta is less than delta T. You see, delta is 4.92, delta 2 is 177. Now for Prandtl number greater than 1, I am taking 10 to the power of 6. So if I calculate delta T, I get, for oils the Prandtl number can be so high. So delta T is coming to be 0.3. So 0.3 is very much less than 4.92. So this gives us the summary of the scale analysis, and the beauty of the scale analysis is that it is giving the Reynolds numbers exponents, the powers it is giving, minus half, minus 1 by 3. Those powers are going to help us in, while plotting my experimental results, I can plot this to the power Nu by Re to the power of half, PR to the power of 1 by 3. I have to get constant, and that itself is a check when I do my experiments, and that constant I can take from my experiments and put it here. Of course, I can do closed form solutions and get these constants. So with this we have completed scale analysis. Now let us move on to what is called as Reynolds analogy. Reynolds analogy. So in the Reynolds analogy, so let's get to the slides in the Reynolds analogy. In the Reynolds analogy, this is the same equations which we had written, the boundary layer equations if you recollect. When viscous dissipation is negligible, we will have k del square T by del x squared plus k del square T by del y squared only. These viscous dissipation terms wouldn't be there, okay? And for flow over a flat plate, dp by dx would be 0, and we will have only mu del squared u by del y squared, and continuity equation is just this, and these are the boundary conditions. Now, when we non-dimensionalize this, we got Reynolds number from momentum equation, and from energy equation we got Reynolds number and Prandtl number. Now, how do I understand this Reynolds number and Prandtl number? What does this mean? What is the meaning of keeping Reynolds number and Prandtl number same? Now let us say I take same shaped body, that is smaller one and a bigger one, okay, same shape, and I am taking velocity v1 with water and velocity v2 with air, and let us say its characteristic length here is L1 and this characteristic length is L2. So this, what we are saying is you get Re1 and Re2 for V1, L1 and ρ1, and here ρ2, V2, L2 is going to fetch you, that is ρ1, V1, L1 by mu1, ρ2, V2, L2 by mu2. What we are saying is that if Re1 is equal to Re2, if Re1 is equal to Re2, not keeping ρ1 equal to ρ2, V1 equal to V2, L1 equal to L2, mu1 equal to mu2, all that I am saying, you adjust these values such that Re1 is equal to Re2, it implies that C of 1 would be equal to C of 2. We will show little while from now how it comes out. So then similarly, if I keep, because why is this so? Because when I non-dimensionalized momentum equation, only Reynolds number came across. So from momentum equation, I am going to get only CF, skin friction coefficient. So if you keep the Reynolds number same, you are going to end up getting same skin friction coefficient no matter whether the fluid is same for both the bodies or not. I mean, they need not be same, the fluids need not be same. As long as the Reynolds number is same, it is okay. But from energy equation, what is that I need to keep same? Not just the Reynolds number, Re1 equal to Re2, I need to keep PR1 equal to PR2. Okay, if I do this, what does that mean? It means that Nusselt numbers also are going to be same. So this is a big boon now. This helps in scaling down or scaling up. If you are modeling a gas turbine blade cooling passage which is hardly 2 mm or 3 mm, you cannot do experiments with 2 mm, 3 mm passage in the lab. You want to scale it up. So you can scale it up by keeping the Reynolds numbers same and using the same fluid in the gas turbine blade passage what you choose in the real life and the lab. So this is, it's a great boon to either scale up or scale down geometrically, but keep Reynolds numbers and Prandtl number same in both the scaled up and the scaled down model. Okay, so this is the understanding of non-dimensional numbers. Whenever we do an experiment, we would like to come up with non-dimensional numbers. Why? Because I can generalize all my results and put in terms of my CF or Nusselt number in terms of non-dimensional numbers. We don't keep dimensional numbers. So now if we just see what is that we got. Now let us see for a given geometry, for a given geometry. U star, that is the non-dimensionalized fluid, that is U by U infinity, if you recollect, is a function of X star, Y star, REL, the Reynolds number. Now, what is tau S? Tau S is equal to mu del U by del Y at Y equal to 0. And if you non-dimensionalize this, you get mu U infinity upon L, that is U star equal to U by U infinity, Y star equal to Y by L. That is what we have done. We have done this in dimensional similarity, so I am just going a little fast here. So, del U star upon del Y star at Y star equal to 0, because when Y equal to 0, Y star is equal to 0. So, you get this as mu U infinity by L. So, now let this be del U star by del Y star is a function of X star and REL. Why Y has gone away? Y star has gone away because I have taken at Y star equal to 0, I have taken one location. So, then Cfx is given by tau wall or tau S upon half rho U infinity square is equal to tau wall is mu U infinity by L del U star upon del Y star at Y star equal to 0 into 1 upon half rho U infinity square. I can replace this with this function. So, that is mu U infinity upon L function F2 X star comma REL into 1 upon half rho U infinity square. So, what is that? I am going to get this as mu by rho is nu upon U infinity L into 2 F2 X star comma REL. So, this is nothing but 2 upon REL F2 is a function of X star comma REL. So, Cfx, as you can see now, Cfx is only a function of X star comma REL, X star comma REL. So, the friction coefficient is function of the location and Reynolds number. This is nothing new for us because we have done this from dimensional similarity, we have done by scale analysis, but let us keep this form as it is because this form helps us in understanding Reynolds analogy. So, now let us write down dimensionless temperature, that is T star is equal to new function which is X star comma Y star. If you recollect, we had taken for Cf U star as a function of X star Y star Reynolds number, but for energy equation, in addition to this, we need to get Prandtl number because that is what we got when we did the non-dimensionalization of my energy equation. So, this is T star. Now, let me write for H the way I wrote for Cfx. H equal to minus K del T by del Y at Y equal to 0 upon Ts minus T infinity. So, if I non-dimensionalize this, I get minus K into T infinity minus Ts upon L into Ts minus T infinity into del T star by del Y star. Okay. So, at Y star equal to 0. Remember, Y star equal to Y by L and T star equal to T minus Ts upon Ts minus T minus Ts upon T infinity minus Ts. So, now I can write Nux equal to HL by K. So, if I substitute this H here, minus K by T infinity minus Ts is gone, minus K by L into L by K into del T star by del Y star at Y star equal to 0. So, this is nothing but this minus has vanished because Ts minus T infinity. So, you have del T star by del Y star at Y star equal to 0. So, now nu x equal to function G2 is a function of, because I have taken Y, this is going to be a function of x star comma REL comma Prandtl number. So, this is for Nusselt number, this is a function, this is for CFX, that is x star and REL. So, REL. So, this is what we get when we do the non-dimensionalization. So, Nusselt number is a function of only location, Reynolds number, Prandtl number, and skin friction coefficient is a function of location and the Reynolds number. So, if I go back to slides, so what is that I am seeing in the slides is that, so I have del u by del x plus del v by del y equal to 0, and this is the momentum equation and this is the energy equation. So, now if I non-dimensionalize this equation, I ended up with Reynolds number in the momentum, Reynolds number, Prandtl number in the energy equation. Now, you see these two equations would look similar when dp star by dx star equal to 0. So, that is what we are going to do it in Reynolds analogy. Then we found that CFX is equal to 2 by REL F2 x star REL. Next, we found that nu x is equal to G2 x star REL PR. Now if I write for nu x G2 into x star REL PR. Now, if I get back, I know that of course Nusselt number has to be a function of Reynolds number and Prandtl number. Now, if I see Reynolds analogy, that is these two equations are similar. Actually, I had Prandtl number. So, if I put Prandtl number equal to 1, these two equations are similar. Then I have CFX equal to 2 by REL F2 x star REL. So, nu x equal to G2 x star REL PR. Now, PR equal to 1 means then I have G2, if PR equal to 1, G2 REL PR would be equal to F2 x star comma REL. So, if that happens, then what is that I have is comparing these two equations, because G2 is equal to F2, I have nu x equal to CFX into REL by 2, CFX equal to REL by 2. So, you get nu x upon REL is equal to CFX by 2. We define Stanton number, ST equal to nu by REPR. So, here this can be considered as Stanton number because PR I have taken as 1. So, I get Stanton number STX equal to CFX by 2. CFX by 2. So, if you just see this, so you get Stanton equal to nu upon REPR, nu upon REPR, nu upon REPR. So, you get Stanton equal to nu upon REPR. So, CFX into REL by 2 is equal to nu x. So, that is CFX by 2 is equal to Stanton number. So, if Reynolds analogy is there, that is for Prandtl number equal to 1, so you get that u star equal to T star and gradients del u star by del y star equal to del T star by del y star. This works very well for even turbulent flows. Remember, we have taken flat plate case where del P by del X is 0. That is mandatory. Del P by del X being 0 is mandatory, and it works even for turbulent flows sometimes, but with a word of a caution. So now if I take laminar flow over a flat plate, so these are my closed form solutions, 0.664 ReL to the power of minus half, 0.332 PR to the power of 1 by 3 Re to the power of half. So I get Cfx by Nu equal to this. So from this I can write that Cfx by 2 equal to Nu by PR to the power of 1 by 3 Re. So if I multiply and divide by PR, both the numerator and denominator, I get Cfx by 2 Stanton into PR to the power of 2 by 3. This I call Colburn factor. So for various situations, we do get this Colburn factor JH, and this works, this form of the equation works well for Prandtl numbers 0.6 to 60. So this equation can be used for flat plate case, for laminar flows, even for Prandtl numbers not equal to 1, that is between 0.6 to 60, it works. And of course, the mandatory thing, as I say again, is dP by dx should be equal to 0. There should not be any pressure gradient. That is possible only in flat plate, and this analogy is not applicable if dP by dx is not equal to 0. So much about Reynolds analogy and Colburn factor. So I think I will stop here and we will take it up in the next module. Thank you.